Alright guys, thanks for joining in and watching the video. I'm just going to review kind of all of the stats concepts that we've started and gone over so far this semester. I got some feedback that particularly the week 8 and 9 assignment that required you to use all of these skills was a little bit difficult for some folks. So hopefully by reviewing some of this information, you'll kind of be more equipped to do that assignment. As you might have seen on Canvas, I am extending the deadline and opening it up so that if you haven't done the assignment, you can submit as many questions as you'd like for partial credit. And if you've already submitted your assignment, you can try to examine areas where you may have maybe chosen the wrong statistical test or struggled, and you can resubmit as many answers as you'd like, to kind of do a redo, so to speak, for additional credit. All right, so let's get going. So concepts that we've learned so far, we've gone over correlations and examining relationships between variables. We looked at z-scores. Those are those wonderful things that I had you guys calculate by hand. And z-scores can also allow us to calculate probability. Those are those questions that I gave you about, how likely is it that somebody could have an IQ score above or below a certain, number, in that assignment on calculating height and weight for kindergartners. We've learned about what statistical significance is and what degree of error and confidence is. And then the two statistical tests that we've really learned how to accomplish are both t-tests and ANOVA. So I'm going to go over each one of these 6 areas, in an overview, but the best I can. Certainly, if you have problems with any of these concepts specifically, feel free to go back to the Canvas module on that specific lecture. You'll find the full lecture as well as all of those helpful YouTube videos that I've posted for each of these, specific areas. Okay, so let's start with correlations. So what in the world are correlations about? Remember that they examine relationship between variables. It comes from, correlation or existing together. And we want to know how the value of one variable changes in relation to another variable. So for instance, I want to know, as the value of my first variable goes up or down, what happens to the value of my second variable? Does it go up? Does it go down? Does it stay the same? All right. So in order to complete correlations, we need to have variable requirements. So we need 2 variables, right? This is a bivariate test. And they need to be at the interval or ratio variable, at the interval or ratio level, and we call those variables this new word called continuous. So if a variable is either an interval or a ratio, we just call it continuous when we're talking about stats tests. So we have 2 variables. They're both continuous variables. If we were to have more than 2 variables, then we go into a different statistical test land, and that's the land of regression. So we just need 2. So example research questions that can be answered with correlations. If my study hours increase, what happens to my GPA? Does attendance to AA meetings decrease daily alcohol use, right? AA meeting attendance being one variable, alcohol use being another. And remember that each of our variables need to be measured in a continuous way, okay? So attendance to AA meetings can be, numbered, 1 to 1,000,000. Daily alcohol use, we would have to quantify it in some way, how many drinks per day, 1 to 1,000,000. All right. So when we calculate a correlation, we get what's called a correlation coefficient. And we denote it using the lowercase italicized r. Remember, R for relationship. And below the R, subset in italics, we write the 2 variables that we're examining the relationship, or that we're correlating, right? So if I'm correlating the relationship between X and Y, I write small italicized r, subset X and Y, okay? If I was looking at a correlation between sound and heartbeat, right, I would italicize R, and then below it I would write sound space heartbeat equals. Okay, and when we get a coefficient, we can use the corral function in order to get the coefficient. Remember that the corral function only can look at two variables at a time, whereas the correlational matrix can look at a whole bunch of different variables and all of their relationships all at once. But the corral function can just look at one relationship individually. So we use the corral function and we get a correlational coefficient that will always range between -1 and +1. It'll never be over or under that range. Okay? So once we find that number, we depict it using the small italicized r, and that's how we denote our results. All right, so remember that correlation coefficients can be one of two things. So they can, we're looking for positive correlations or direct correlations, and that's when variables change in the same direction. So if my first variable goes up, my second variable also goes up. They're changing in the same direction. If my first variable goes down, then my second variable also goes down. They're changing in the same direction. That makes it a direct correlation or a positive correlation. One way to tell if you have a positive correlation is to look at that correlation coefficient you just calculated via either the corral or the correlational matrix function. And we're looking for a coefficient that's positive, right? So positive correlation, positive coefficient. So you're looking for 0 to +1. Whereas the other alternative is a negative correlation, or what we call an indirect correlation. This is when variables change in the opposite direction. So if my variable A increases, my variable B decreases, or vice versa. Variable A decreases while variable B increases. They're going in the opposite direction. And that's depicted by a negative coefficient. So when I use that corral function or my correlational matrix, I'm looking for a number that's below 0. It'll be negative, right? So negative correlation, negative coefficient means it's indirect. So remember that the important thing to remember with correlations is that they have a direction, right? They're either direct or indirect, and they have a strength. So we have strong correlations and weak correlations and a whole bunch of stuff in between, okay? So we can determine our direct or indirect correlation by either a positive or a negative coefficient. How do we determine the strength of the relationship? Well, again, we look at the coefficient, but we look at it a little bit in a different way. So here, a strong correlation or a perfect correlation would be depicted by a coefficient that's 1.0. Now this can be both positive or negative, right? So it can be +1 or -1 means it's a perfect correlation. This means that your two variables, right, variable A and variable B, line up and overlap 100%. That means that they're the same, right? In a weak correlation, the coefficient will always be 0. And that means that there's absolutely no overlap or no relation between variable A and variable B. And so there's a whole bunch of stuff in between, right? There's strength of coefficients exists on this continuum from strong to weak. And so in your book, there's a handy dandy chart, and it'll tell you if the size, the coefficient is between 0.8 and 1, then we use the term very strong to describe it. If it's between 0.6 and 0.8, strong, et cetera, et cetera. Now it's important to remember, again, here these numbers can be positive or negative. So if my correlation coefficient is negative 0.24, right, it would fall in this group here in the 0.2 to 0.4 range, even though it doesn't specify positive or negative. But these can be positive or negative. So you can have an indirect strong relationship, or you can have a direct strong relationship. It just depends on whether your correlation is positive or negative, and it would be between these numbers, right? Okay. So using the corral function to get a correlation, we use CORREL, and then we select our variable A and our variable B. So let's skip over to Excel real quick. And let's do an example. So I'm using the data set. What in the world is this called here? This is called, oh, go away, Apple. This is the data set, the 382 survey data with codebook that we used for week 7. And this was the one that I made you guys take a SurveyMonkey, and you answered a whole bunch of questions about, you know, where you currently reside, how happy you are, your friends, your family, your sleep, you know, all that stuff. And I'm just using this for example. All right, so let's say that I want to run a correlation. Let's say I'm interested to see if happiness correlates with your friend variable. What I could do, I'll go over here. I'll use the equal sign, CORREL, right? Open parenthesis. I will highlight my first variable, which is happiness. I will use a comma, and then I will highlight my second variable, friends. So what this does is this just spits out a correlation coefficient. So I have a positive number, 0.29, 236, you know, whatever. So a positive 0.292. And so if I were to go back to the, you know, the lecture here, right, my correlation is positive, which means it's direct. So that means that my variables are changing in the same direction. As happiness goes up, my number of friends goes up. And then if I wanted to look at strength, so what did I say my coefficient was? 0.29. So 0.29 falls in this range here. And so it's a pretty weak relationship. Even though it's direct and the two change, you know, accordingly, it's still a fairly weak relationship. AKA, there's not much of a connection between your happiness level and your number of friends. Okay? So we can use the corral function to find correlation coefficients, as well as the data analysis tool pack using the correlation matrix. So let me give you an example of how to use that. So going back to my data, let's say now instead of just looking at happiness and friends, I want to look at all of these variables: happiness, money, friends, family, whether my needs are met, how much sleep I'm getting, my self-care. So what I do is I go under the data tab. I go into my data analysis tool pack over here all the way on the right, and I select the correlation option and hit OK. All right, so what variables am I interested in? Well, I just said I'm interested in everything from happiness to self-care. So I go ahead, I just click and drag, I highlight all of the stuff that's in between those boxes. Now, let's say that on my my spreadsheet, all of my variables weren't close together and grouped like this. I can use the control function. So let me just delete this. Let's say that I was interested in happiness and, you know, just self-care. I could highlight happiness, then I could hit the control function. I could highlight self-care. I could highlight family. So the control function allows me to separate my boxes here. But in this case, they're all close together. So let's just highlight them all here. Okay, so I've selected my input, and then it's asking you how they're grouped by columns or rows. So basically what they're asking, are my variables going this way in columns, or are they going this way in rows? And as you see, our different participants are in rows, our variables are in columns, so we want to keep the columns selected. And did we put our labels in our first row? Yes, we did. We included our labels. So we click this box here. And I'm just going to put it in a new worksheet because I don't have room anywhere else on my spreadsheet to put it. So I'm going to hit OK. All right, so if we've done it correctly, our new sheet should have this nice little correlational matrix, right? And we can see here that it included all of the variables we wanted, and because we put our labels in, it labeled it nicely for us. Okay, remember that you're always going to see this diagonal line of ones. The reason for that is because if you look, the 1 will always exist in the box where the variables line up and match. So sleep to sleep is always going to be a perfect relationship, right? Because they're totally the same. So that's why it's depicted by a 1, aka a perfect relationship. Everything else will spit out these correlation coefficients. So let's say for funsies and giggles, I care about friends and whether my needs are met. I would look in this little box here. I can tell this is a positive number, right? A positive correlation, which means a direct relationship. As one goes up, the other is going up. Um, and it's 0.4, which falls into, on my chart, this moderate area. So I have a moderate direct relationship between friends and needs. Okay, so that's how to use both the Correll function and the correlational matrix to look at correlations. All right, moving on to z-scores. So z-scores, what in the world are they? Well, and let's represent this. So remember that a z-score tells us where a value falls on a normal distribution. If you remember, a normal distribution has a few properties, right? It's symmetrical, the mean, median, mode are the same, has asymptotic tails, all of those nice little qualities, right? So a z-score tells us where on the curve a value falls in relation to the mean and standard deviation. So when we're plotting a curve, we have the option, we can do the raw score, right? The raw mean, the raw standard deviation, or we can just kind of depict it in this standardized way where the mean is 0, and then we have positive standard deviations to the right, negative standard deviations to the left, right? All we want to know is, where does our score fall? So here I've given a score of like 107, right? If we can see that on the raw score. The z-score is the value that's down here, right? It's somewhere between 0 and positive 1 standard deviations. We're just not sure exactly where. We would have to calculate the z-score in order to do that. Oops, and I just hit the wrong button. All right, so why do we use z-scores? There's two reasons. So z-scores allow us to compare data sets that were not measured in the same way. So for instance, if I'm measuring high school performance, I can measure it via ACT scores, or I can measure it via GPA scores. If I just had ACT and GPA scores next to each other, I wouldn't know how to compare or contrast them, right? They're two totally different scales. One is from 0 to 4, the other is from, 0 to 29, 30, whatever, I forget what ACT scores are. But they'd be difficult to compare. Now, if we converted all of those scores into z-scores, where they're just, values in relation to the mean and standard deviation, that's what makes them comparable. So that's one major reason why we use z-scores. The other major reason to use z-scores, and I'm skipping ahead on my lecture here, is to calculate probability of a normal distribution, and to calculate those questions like, how likely is it for someone to? I gave the IQ example. I asked you to calculate percentile of height and weight in one of your assignments, right? Z-scores allow us to answer those types of questions. But it's important to know how to calculate a z-score. So the z-score is calculated with this formula, where x represents your value, x bar is the mean of your sample set, and then s or sd is your standard deviation, right? So this is the number we're trying to find the z-score from. We subtract the mean and we divide it by the standard deviation. So let's say that I received an ACT score of 27.5, right? This is the value here that I'm trying to calculate. I would need to know my mean and standard deviation for the ACT, which I happen to. The mean for ACT is 21. So first I subtract 21 from 27.5. I get an answer of 6.5. All I do is I divide that by the ACT standard deviation, which I know is 5.2, and I get my z-score positive 1.25. Remember that your z-scores are usually going to fall somewhere between negative and positive 4. So you're going to get a number between 0 and 4, either positive or negative, for the most part, because most of the curve is covered kind of within that range. Okay, so we've already covered that. So remember that when you're calculating probability, your steps, you need to first calculate your z-score, and then you're looking at what percentage of the curve falls above or below your z-score. And so I gave you the handy-dandy unit normal table that you can calculate. So this is in decimal form, how much of the curve falls in each portion. In order to calculate this to a percentage, you would just move your decimal point over 2 spaces to the right. So for instance, if my z-score was 0, aka my mean, right, 50% falls below, 50% falls above, right? Because B is below, C is above. All right. I probably won't ask you any more questions about calculating percentage. I know it's kind of painstaking, but I just want to make sure that you all kind of get a general idea on how to do that, right? So you calculate your z-squared first. You determine whether or not the question is asking you about the portion above or below your z-score, and then you use a unit normal table to find the percentage above or below the curve. All right. Moving on to significance and interpreting statistics. So when do we go ahead? So remember that because we can never, ever, ever be 100% certain of anything, right? The world is too complex to say anything for real for certain. We need to kind of make a threshold for when do we go ahead and conclude something's happening, we're observing a phenomenon, I think there's something going on here, right? And in the world of statistics, we've determined that we want at least 95% confidence before we go ahead and accept our research hypothesis and say, I think there's something going on here. So remember that confidence and level of error are two kind of similar concepts. They're the opposites of one another in the sense that your confidence and your level of error will always add up to 100%. So if you so it's not like they're opposites, they're kind of like mirrors of one another, if that makes sense. So as my confidence goes up, my level of error goes down. As my level of error goes up, my confidence goes down. So we want at least 95% confidence that what we're observing, our results from our statistical test, are due because of a phenomenon and not just out of a chance of error or randomization or probability, right? So the way that we look at our level of error and our level of confidence is to look at the p-value, right? The degree or level of error is depicted as a p-value, otherwise known as probability of error. That's why it's called p, probability of error, okay? So if we want a level of error that's less than 5%, then we need to look for a p-value that is less than the decimal form of 5%. So moving on to the next slide. Goodness gracious, this computer. There we go. Okay. So when I do a test, right, like either a t-test or ANOVA regression, it's always going to spit out a p-value. This is the probability that the phenomenon we're examining or testing is due to chance. Because we want less than 5% chance, we need a p-value that's less than 0.05. Remember that when we're converting decimals and percentages, we move the decimal over right 2 places to get the percentage. So if we want 5%, it's 0.05, not 0.5. That's a very common mistake. It's 0.05 is the p-value threshold, okay? So when we run our test, what we care about is our p-value less than 0.05? If it is, then great. We have a smaller degree of error than what we need, what our threshold is. That means that we can reject our null hypothesis, otherwise known as accept our research hypothesis. We can say the thing that we thought was happening is definitely happening, right? Something's happening here, something's going on. You know, it's so clear that this can't just be due to randomization, it has to be true, right? If our p-value is above 0.05, then we're forced to keep the null hypothesis. We just can't determine with certainty that what we're observing is outside of chance. It's just too high of a degree of error. It's over 5% degree of error, okay? So this is very important. If I were to argue that out of this whole slideshow, this by far is the most important slide. So please make sure you understand this part about p-values, degree of error, and when to make decisions about accepting or rejecting your research hypothesis, okay? All right, so this gets important for when we're doing t-tests and ANOVAs, right? So t-tests, let's review what they are. So t-tests are when we're looking to compare group differences. So t-tests compare the average scores of two groups and determine whether or not there's a difference. There's two types of t-tests. There's independent t-tests and there's dependent t-tests. What's the difference? Well, in an independent t-test, groups are autonomous of each other. That means that a member cannot be in two groups simultaneously. They have to be in either one or the other. So for instance, gender, if we're measuring it in a, pre-2020 concept way, you are either male or female, right? You can't be both or in between. That means that this grouping is independent. The other option is a dependent, or what's called a paired samples t-test. This is what we use when the same group is either, when there's one group of participants and they're measured twice, or if there's potential for overlap in participants. So let's say that you could be in both groups at once, depending on how you phrase your question. Then you have to use a dependent samples t-test, okay? So when conducting a t-test, the first decision you have to make when looking at the question is, does this call for an independent t-test or a dependent t-test, right? Are my groups different or potentially the same? When do we use a t-test? So I just gave you the example, male versus female for independent groupings, undergrad versus graduate, pre-test versus So male versus female and undergrad versus graduate are both examples of independent groupings. Pre-test versus post-test would be an example of a dependent t-test, right? Because it's one group of people being tested twice. We use a t-test when our independent variable is what's called nominal or categorical, right? So gender is nominal, male versus female, right? Graduate status, nominal. Testing status, nominal, pre versus post. There's different groupings within the independent variable. Our dependent variable is going to be continuous, right? So any sort of, when we're looking at differences between males versus female on stress has to be a continuous variable. Males versus female on rates of depression has to be a continuous variable. And remember that for t-tests, we can only have two groups. We cannot have any more than two. T-tests are always two groups. And like I mentioned, our dependent testing variable is always a ratio or interval, what we call a continuous variable. All right, so the first decision we had to make was whether or not our test calls for independent or dependent t-test. The second decision we need to make is, are we testing a hypothesis that's directional or non-directional? So remember that any t-test, whether independent or paired, can be run as both a one-tailed or a two-tailed test. Basically, the difference between the one-tail and the two-tail is whether or not we're looking, whether or not we put kind of all of our eggs in one basket and say the error is going to be on one side of the curve, or if we're saying, well, we're really not sure, we need to account for the potential of error in both directions. So we determine the use of a one-tail or a two-tail test based off of the direction of our hypothesis. So as an easy cheat sheet, when we have a non-directional hypothesis, then we use two-tail. When we have a directional, we use a one-tail test. And I think that actually was on my slide, but it's not showing for some reason. So two-tail tests, non-directional. For a directional hypothesis, we use a one-tail test. Okay. All right, and then the third decision we need to make when choosing a t-test is whether or not our variable has, or whether our groups have equal or unequal variance. So this is when you have to use the variance function in Excel to calculate variance for both of your groups. So let me show you real quick how to do that. So let's say, so going back to my example data sheet, so I've actually included it here. But let's say that I didn't. All right, so let's say that we were looking at, we wanted to know whether or not internship status of internship status influences happiness, right? So here I have people that are in their internships versus people that aren't in their internships. So I would want to take both groups and look at their happiness and calculate their variance, right? So here I've used the equal var function. I've selected my group 1 happiness scores, and I've calculated, oopsie poopsies, I've calculated their variance. And I just messed it up. Okay, so I just select group 1, their happiness scores, and I get a variance of 4.02. I do the same thing for variance of my second group, happiness score, right? And I get a result of 0.9. So when comparing variance, you want to use your best judgment. If they're close in number, then you can assume equal variance. If they're really not close, assume unequal variance. So here I have a variance of 4 versus less than 1. I'm going to say that those two numbers are different enough, right? If they were 4.0 and 4.8, I would say they're pretty close. They're within, one point of another. But here they're a few points apart. And so I'm going to say that they are unequal. So that means that we need to choose a t-test that assumes unequal variance. Okay? So the first choice was independent versus dependent. My second choice was, do I need to run a 1 or a 2-tailed test? And my third choice is, am I assuming equal or unequal variance? So which test do I do based off of those decisions? In my statistical toolbox, there's 3 t-test options. And I'm kind of giving you a cheat sheet here for which one's which, right? The paired 2-sample for means, right? A paired t-test is another name for a dependent t-test. So this is what you use whenever you have one group of people that are tested twice, or if there's overlap in your tests, in your groupings, okay? If you have an independent test, then you have 2 options, the 2-sample tests, and here's where you choose whether you have equal or unequal variance. Now, a thing to notice, in dependent tests, we actually don't care about variance. So if you determined early on that you have a dependent t-test, you can actually skip the step of looking at variance. But, I always just say there's 3 steps. That way, never hurts to have the answer to the question before, just in case you need it. Okay, so these are the 3 options depending on what you chose. So gender, so let's say running with my example of internship status and happiness, I have independent groups. I'm going to assume unequal variance. I would choose this last option that's called t-test, 2-sample assuming unequal variances, and I would run my t-test. Whenever you do a t-test, it's so this would be, so this is the example dialog box that you would get. Whenever you do a t-test, it always spits out a results section that looks something like this, right? So it'll always depict your variance. This is a good way, if you've gone in your Excel spreadsheet and calculated your variance, compare your numbers here. Make sure that you selected the right groups. These should match the variance that you calculated earlier when determining unequal versus equal variance. Okay, but numbers that we're actually concerned about, we can care about the degrees of freedom, and that's because we have to report this number in our final results. The degrees of freedom is always the 5th option down. It's labeled by lowercase df. The next number we really care about is our t-stat. This is the finding of our t-test, right? The t-score that the test spit out. Here it's negative 9.38. The other thing that we care about is the p-value. And now here's where our decision about a 1-tail versus a 2-tail test kicks in, because there's actually 2 different p-values that every t-test gives you. There's the p-value for the 1-tail test, and there's the p-value for the 2-tail test. So let's say that I was running with a directional hypothesis, and I care about the 1-tail test. I would use this number here, and it's 7.56. If I was running with a non-directional hypothesis, I would use the other option. So remember to look in these places for your critical numbers. It's very tempting to look at some of these other numbers or to confuse them. The t section, which we really don't care about, that's the critical t-value. Remember that the found t-stat has to be higher than the critical t in order for it to be a significant result. You could look at them that way and determine whether or not you're significant, but it's more accurate to just report the p-value. So here the p-value is 7.5. It's way, way, way above 0.05, and so we already knew it was insignificant, right? All right, so those are the key places to look for a t-test. Remember that the t-score alone does not determine whether or not we accept or reject our research hypothesis, because it doesn't give us significance. The only thing we care about in order to determine significance is the p-value, right? And so we go back to this very, very important slide where if the p-value is less than 0.05, then we can reject the null, we can accept our research hypothesis and say something's happening. If our p-value is above 0.05, we have to keep the null. We have to say there is no difference between our two groups. So remember that when we're reporting a t-test result, it's in this standardized format. It's a lowercase italicized t. In the parentheses, we put our degrees of freedom, right? I said that was an important area to look. We report our found t-value, and then we put our p-value. T represents the test used, 28 degrees of freedom. This is our obtained value. Otherwise, on our results, right, the 3.01 coincides with this number here, the t-stat, right, the found t-value. Which here they don't match because I use different, I'm just mixing up slides. And then p-value is either that one-tailed or two-tailed p, depending on what type of test you're using, okay? So here, if my p-value is 0.01, it's below 0.05, and I would say that this is a significant, statistically significant result. I could confirm my research hypothesis. If the p-value is above 0.05, then we cannot confirm our research hypothesis. We have to confirm the null, which means there's no difference, right? Okay, so that's t-tests in a short. Let's see. And we can go to ANOVAs. So remember that for ANOVAs, this is when we have at least two groups or more that we want to compare, right? So when we have two groups that we want to compare, we use a t-test. When we have more than two groups, we use an ANOVA. We test them simultaneously. And we want to see whether or not the means of the groups differ from one another on a particular score, right? It's also called an F-test, and so it's depicted by the uppercase italicized F, and that's for the guy Fisher who created the ANOVA. So there's different types of ANOVAs. For the purpose of this course, remember that I said we are always going to be using what's called a one-way ANOVA, or otherwise known as a simple ANOVA or single factor ANOVA. Basically, the single factor just means that we're grouping our variable in one way. We have a grouping variable, otherwise known as our independent variable, and then we have our continuous dependent variable. So here we're interested in practice times of swim meet performance. So practice times is my continuous dependent variable, and I want to know whether or not, I'm concerned with the time of their swim, right? Their clocked time, that's my continuous variable. And I want to know, does practice improve their time, or does practice make an overall difference in their time? And so I've grouped people based off of how many hours a week they practice. That's my single factor grouping variable, otherwise known as my independent variable. Okay. So our standard reporting format for the ANOVA looks pretty similar to the t-test. Instead of t, it's F. Instead of 1 degrees of freedom, we have 2 different degrees of freedom. We have our degrees of freedom between groups, and then we have our degree of freedoms within groups. And I'll go over this a little bit more. We have our obtained F value, and then we have our obtained P value, right? Remember, the P is the probability that the null hypothesis is true, aka that our results are due to chance. This is the standard format for reporting. For degrees of freedom, there's not just one calculated degrees of freedom, there's 2. So there's the between group estimate. This is the first number you put on your standardized format, and it's the number of groups minus 1. So if I have 3 groups in my example, I'd subtract 1, and I'd get a degree of freedom of 2. let's say that I was comparing a certain score based off of racial identity, and I had 6 different options for racial identity. I would take 6 minus 1 for an answer of 5. And then the second number I report is my within group estimate. So this is the total sample size minus the number of groups, aka how many participants or sets of data do I have within all of my groups. So let's say that I took the score, the swim times of 36 different swimmers. I grouped them by 3 different groups, right? So 36 minus 3, I would get a within group degree of freedom of 33. This is the second number that I report. So going back to my example, I report 2, 33. So remember that ANOVAs are looking for overall difference, right? So we have to keep in mind what our null and our research hypothesis is for each ANOVA that we run. So a null hypothesis for an ANOVA, it usually reads something like, there is no difference between the means of my X amount of number of groups. A research hypothesis is that there is an overall difference between the means of the groups. So sticking with the practice time example, right, practice time does not make a difference for swim time, or alternatively, there is an overall difference in performance based off of their practice time. Okay. And remember, because we are always concerned with the simple factor or single factor ANOVA, when we're running our ANOVAs with our data tool pack, we always want to select the first option, the ANOVA single factor. We will never use these 2 tests in this course, the other ANOVA options. So what do I mean by that? So if I'm in Excel and I want to compare multiple groups, which I don't have a great example here, but let's say I did, in my data analysis pack, just like there's different t-test options, there are 3 different ANOVA options. I will never use the last 2. I will always use the very first one. That's ANOVA single factor. Okay. All right. So ANOVA will spit out so when I use the data analysis tool pack to run an ANOVA, it'll spit out results that look something like this. The first box just kind of summarizes how many people were in each of my group, what the sum scores were, the average scores, and the variance in each of my groups. What I'm really concerned about is what spits out in the second box. So this is where I find my degrees of freedom for both between group and within group. So they're listed here, right? So degrees of freedom between groups, that's the first number I report in the little commas. The within group, 33. And then where do I find my F stat? It's always in the right side over here and underneath the capital F. And then here, there's just one p-value, and it's labeled a p-value 0.85, right? So I'm interested in this number, as well as the degrees of freedom. Everything else I could really care less about. So I take those options and I report them in the standardized format. And remember that based off of my p-value, I then determine whether or not I'm accepting my research hypothesis, or if I'm sticking with the null, if there is a difference or is not a difference between the groups. Okay, so the last thing that I'm going to include on this summary video is how to choose the right test. So if this is something that you're struggling with, so one of the tools that the book gave you was this little flow chart, right? So are you examining relationships between variables, or are you examining differences? You know, so you can go through and ask yourselves these questions. If you don't find this particularly helpful, which I'm honest, I don't, I've given you here a little cheat chart. Okay, so this chart, this is how you use this, right? So you can either look at the question itself and look for keywording, right? What am I seeking to do? Am I examining relationships? Am I comparing scores and looking for differences? Am I comparing and looking for overall differences? Or am I trying to predict a score or an outcome, right? Or the other thing that I can do is I can look at what are the variables that are given to me. So here you can see that for the first example, for the correlation, I need a dependent variable that's continuous, aka a ratio or an interval, and my independent variable also needs to be continuous, right? So if I'm given two continuous variables, none of these other options have continuous variables, as an option. Well, except regressions, but we haven't learned how to do that, so that's easy so far, right? We don't know how to do that. I'm probably not asking you to do that. So if I'm given two continuous variables, this is my only option, right? I must be doing a correlation. If I'm given a continuous dependent variable and a nominal or categorical, right, a grouping independent variable, I might be looking at a t-test or ANOVA. The only thing that differs a t-test versus ANOVA are how many possible options are available within the independent variable. So for instance, is my grouping variable gender, and I have two options, male versus female? Or is my grouping variable gender, and I have five options, female, male, non-binary, other, right? That would indicate that there are three or more options. So depending on the number of options that are available within the independent variable, or aka how many groups I have, that determines the t-test versus ANOVA, right? And the last example, which I'm hoping we're going to be able to get to this semester, is the regression. That can use either nominal or continuous variables in either of these categories, but the key factor is that regressions calculate many, many more variables than just, a handful. So we're talking like 7, 8, 10, 12 different variables are at play for the regression. Okay. All right. So this is a helpful chart. Feel free to use it for the practice assignment. Go ahead and consult the the Canvas posting that I put for your assignments. Make sure to check in with your groups. Otherwise, check my announcement for office hours. If you have any questions about this content, feel free to ask. All right. Hang in there, guys. Thanks so much for listening.